3 o'clock. Heart rate. I hope everyone didn't drop. Man. That's all right. Well, either way, I got to teach because lots of people look online, so. Anyways, well, welcome to Chapter 9. So some timeline stuff. Week from Wednesday, we're having the test for chapters 5, 6, and 7. So today's stuff will not be on the test. And Monday, so a week from today, we'll do a review for the next test. And then we'll have an easy week. Oh, actually, after that, we'll only have 2 more weeks. So Thanksgiving, and then we'll have the end. Dun dun. Or will we? Let's look at the schedule. Maybe I'm off by.
2 more weeks after.
Oh, good. Well, lots of Thanksgiving. Oh, yeah, you're right. 2 more weeks. So, oh, but Veterans Day is off. So we got the 7th, the test, and Veterans Day. So we'll have class on the 14th. And then we'll have week after Thanksgiving. You're right. So which is good. We'll have lots of time to study for the final. So anyways, does anybody have any questions on anything before we start? Any questions about the test? Nope. Okay. And I like to point out today is the last day to drop any class, and of course I think the drop period ends at 4 o'clock, so which is in the middle of this class. So if you want to do it, you better do it now. Not this class, of course. No one ever dare drop chemistry, of course. But or our classmates. Anyways, so we're pushing on to chapter 9. So chapter 9 deals with chemical bonding. The 3 main types: ionic, metallic, and covalent. So, ionic bonding, all right, we just increased by 33%. And why do things bond? This is the straight answer. Things bond because it's lower energy. So what happens is in a group of molecules, when a group of atoms come together and with their electrons and their nuclei, they interact, and they interact in a fashion. If it happens to be that they can find a configuration that's lower energy than them being apart, then the bond will form. They'll bond that way. And if it doesn't form, then or it can make well, if it's not lower energy, then it's not going to form, basically. And there are lots of rules, and we're going to learn some of the rules now about how it bonds. But these are general rules. That's the overall rule. If everything comes together and if it can organize in a fashion that it bonds, it will form. So, but I do mention a little bit of physics in this class, but this is Coulomb's law. Force is equal to a constant, Q1 charge of 1, Q2 charge of a second, over the distance between the two squared. So this is just like gravity. Gravity is mass of 1 over mass of 2 over distance squared, but it has gravitational constant, which is much, much weaker than the Coulombic electrostatic force. So let's go to ionic bonds. Ionic bonding is when one atom gives electrons to the other atom, and then they bond by unlike charges. So in this case, it's you have the purple sodium atoms give the electrons to the green chlorine atoms. The sodium becomes sodium plus 1. The chlorine becomes chloride minus 1. And then the unlike charges attract and the like charges repel. And the magnitude of that attraction and repulsion is described by that equation. And really, ionic bonding is easy. You can do it all with Coulomb's law and geometry. That's all you need. But that would be a very boring class. Here's metallic bonding. Metallic bonding is also very easy. It has to do a little bit more higher math, but we understand it pretty well. Metallic bonding is just a sea of electrons between some positive nuclei. And then the hard stuff is a covalent bonding, which you have equal sharing or unequal sharing in polar covalent bonding, and there's lots and lots of stuff. We'll spend most time on covalent, but it is by far the hardest. The other two, ionic bonding, you can do all, like I said, you can just use high school geometry and Coulomb's law. You can figure out everything else. And metallic bonding, it's you have to do a little bit of quantum, but it's pretty easy quantum. Covalent bonding, that's tough stuff. We'll get into that much more later. But I want to talk about this. So we're going to talk about ionic bonding very briefly. Well, I guess the most of today's class period. Then we'll just talk about covalent bonding more or less after that. So lattice energy. So imagine kind of a bunch of free sodium and chloride, sodium ion and chloride anions all floating around in space. And then they organize themselves to form a crystal of sodium chloride. When it does that, a certain amount of energy is released, and we call this the lattice energy. So, and this is something we've never really observed directly, but we can do it by something, by delta H being path independent. Remember we talked about enthalpy being path independent? Well, we can do this, and this is called the Born-Haber cycle. So let me go over each step. We start off here with sodium metal, sodium solid, and chlorine gas. So half a chlorine gas to make sodium chloride. And the y-axis here, this is energy. So the elements sodium and chlorine are higher energy than sodium chloride. So this is an exothermic reaction. I will show you this exothermic reaction with my elements in action. Here we go. That's Theodore Gray right there. Guy's nuts. So there's sodium. He's melting the sodium, and then he's turning on the chlorine. So there's the chlorine. And there it goes. So it's on fire.
I'm going back.
That's forming sodium chloride.
Okay.
And then he comes up, he uses to salt his eggs. So the guy's nuts. The point of the story is that, and this did this last class too. Yes, nothing like Netflix telling me there's cool things to watch. So it's very exothermic. So sodium metal plus chlorine gas making sodium chloride is very exothermic, and it burns. So we think of fire. Oxygen is the most common oxidizer in fire. You need oxygen for things to burn. Things can burn, and other than oxygen, chlorine is one of them. So we start. So rather than we can just burn it right away and get this, but since we have path independent nature of enthalpy H, so we can break it into steps. So sodium solid can go to sodium gas, and then chlorine, Cl2, can rip apart to form Cl gas. And then sodium vapor gas, sodium gas, can lose an electron to form Na+. And then, I'm not tall enough to point up there, then this step here, the electron from sodium can be added to chlorine, and that's in fact endothermic, releases energy. So, and then now at this point in time here, we have sodium plus ion vapor and chloride anion vapor, and then it can go down in energy there. And then this step number 5 I've listed is known as the lattice energy, which is right here. So the lattice energy of a compound. So we actually don't ever measure this directly. We form it that way. And the overall reaction is equal to, so this delta H right here is equal to this step number 1, 2, 3, 4, 5. Add them all together. Or if you want to look at it the other way around, the lattice energy is the step number 5. We're looking 5. 5. Lattice energy is number 5, which is delta H minus the 1, minus 2, minus 3, minus 4. Like so. So this thing right here is equal to that. Well, not necessarily that, but the delta H minus this, minus this, minus this, minus that. So we can calculate it out that way, and that's how we do it. So let's go ahead and do that, and let's talk about the lattice energy, how it changes. So let me remind you of Coulomb's law yet again. Force is equal to some constant, charge of 1, charge of second, over the distance squared. So which means a bigger charge means a bigger force, or a smaller charge means a smaller force. Also, a bigger distance, a smaller force, because it's 1 over r squared, or a closer distance means a stronger force. So let's look at this. And here we have chlorides. We have lithium chloride, sodium chloride, potassium chloride, and cesium chloride. And as we go down the periodic table, they get bigger. So lithium is the smallest, sodium is a little bit bigger, potassium's a little bit bigger, cesium's a little bit bigger. So what we should expect is, as this distance between the charges increases, the force goes down. Or as the distance gets smaller, the force goes up, and that's exactly what we see. So lithium with the tiny distance has minus 834. Cesium with the bigger distance has minus 657. But at the same time, if you look at that, that doesn't change that much. I mean, it changes, but it's not a really big effect. Let's compare charges. So here are two things. We have sodium fluoride. Sodium fluoride, the distance between the nuclei there is about 231 picometers. And calcium oxide, the distance there is about 239 picometers. So about the same. So if you have about the same, and it's, so the force equals a constant times the charge over the charge of 1, charge of 2, over the distance squared. If the distance squared is the same, and the constant, of course, is the same. So we have plus 1 minus 1. Plus 1 times minus 1 is minus 1. Plus 2 times minus 2 is minus 4. So we'd expect then the force to be about 4 times the size. And if you see here, sodium fluoride minus 910, calcium oxide minus 3414, and 9 times 6 is 36. So this is about 4 times the size of that. Why is it not exact? Because this is 239 picometers. It's slightly bigger. If it's slightly bigger, it's going to be slightly less than 4 times, which is what we see. So what does this tell us? The charge is more important for ionic strength. Size is important, but it's not that important. But charge is the biggest indicator of ionic strength. And what else with this? The stronger the ionic bond, the less soluble things are. So if you remember from chapter 4, we talked about, as I mentioned this as well, that the things that are soluble, alkalis, all plus 1. And they're big ions, so they're plus 1 and big ions. Things that are insoluble, like phosphates and carbonates. Phosphates are minus 3, and carbonates are minus 2. So those things, those tiny charges that are very strong, they are not soluble. They don't break apart. Also, salts in general, they're hard to melt. So has anyone ever melted salt before? I haven't. I mean, I've taken salt and hit it with a blowtorch. It just glows red. It doesn't melt. So it's hard to melt salt. You can melt salt. It just takes a lot of energy. Okay, so Arrange these compounds in order of increasing magnitude of lattice energy means low to high. So let's look at these. And let me put the charges here. Calcium is going to be +2, oxygen is going to be -2, potassium +1, bromine -1, potassium +1, chloride -1, strontium +2, oxygen -2, like so. And what that means is that the low to high, the low ones are going to be the KBr and the KCl, and they're going to be less than calcium oxide and strontium oxide. So how do we arrange them? So let's start over here on the left, and we look at KBr and KCl. So the bigger one was going to be lower energy, or the smaller one is going to be higher energy. And if you look at the periodic table, here is chlorine, here is bromine. Bromine is lower, therefore bromine is bigger. And if bromine is bigger, it's going to be the lower energy. So we're going to put bromine there on the far left, and then chlorine there next, and then that symbol there. So does everyone understand the logic there for calling KBr less than KCl? Questions with this? Same idea looking at the strontium and the calcium. If you look at the periodic table, so calcium is here and strontium is there. So calcium is above strontium, so that means calcium is going to have higher lattice energy and strontium is going to have lower. So then we arrange them as such. So strontium goes there, calcium goes over here, and I'll just go ahead and put the there. So that way, from low to high, we have the +1, -1s first, and we pick the biggest ion. In this case, potassium is the same, so it's the bromide or chloride. Bromine's bigger, so it's first. But they're both smaller energy than the +2, -2. Oxide is the same, so we look at the alkaline earth ion. Strontium is lower than calcium, therefore it's bigger, therefore it's lower energy, and then calcium is the highest there. So, questions with this? So, which one of these has the highest energy? Highest lattice energy. So I'll go ahead and give you the charges. I think it's A, sodium chloride. I think it's B, vanadium 3 oxide. I think it's C, tungsten carbide. Okay, so everyone, 100%. It's going for that. It is, tungsten carbide is the correct thing. It is the strongest ionic bond. Does anyone have tungsten carbide rings? They can sell these as rings. This is a very, very durable material. It's so durable, in fact, that you cannot break it with the jaws of life. See, the jaws of life they're these clippers that the firefighters and ambulance workers have. They can cut people out of cars. So tungsten carbide will not be clipped by the jaws of life. Can you break tungsten carbide? Yes. You can use a diamond saw. You can use a laser. So, but it's a really durable material. People like it in rings because it's cheap, it's shiny, and it's really durable, so they don't scratch as easily. Problem is, like say you're working on your car and you get your hand stuck in your car, they have to rip apart the car to get your hand free. So you can't go and snip the ring unless you want to cut off your finger. So it's shouldn't use it if you have a chance of getting your hand caught in something. What they use this stuff for, tungsten carbide, It's used on the inside of tokamak fusion generators. Do you know what a tokamak is? Look like a donut. It's like a. You ever seen the movie Iron Man? It's the first one. They had the arc, whatever the heck it was called, arc thing. It's a tokamak. That's really what it is. And it's one of our fusion generators. It's a Russian made. They call it the Russians make the tokamak. We have 3 proven types of nuclear fusion generators. We have the National Ignition Facility in Livermore, where there's only one. There's a couple tokamaks around, and then there's thermonuclear devices that can make fusion. But those are the only proven technologies we have. And in the tokamaks, there's tungsten carbide in the center. So they can handle that amount of energy from that nuclear fusion. So it's really tough material, to say the least. So I wouldn't have a ring like that. I'm too afraid of it. I mean, they're pretty and they're cheap, but I like my metals. Okay, so what else do we use ionic compounds for? So this is part of my chemistry and society talks to try to give you, so what do we care about chemistry? Because it's useful. So silver nitrate is an ionic compound, and we use it as an antimicrobial agent. It's particularly tough for me because it turns skin brown. So if I, as a Caucasian, if I touch the stuff, in sunlight, you go in sunlight, it will turn your skin brown. And my dad's a chemist, and we had a pretty big jar of the stuff in our basement when I was a kid, and whenever I touched the stuff, it turned my hands brown. It takes a long time, too, because you have to wait for your skin cells to regenerate to get rid of it. But the good thing is it's very antimicrobial. So it's used for that. There are some Band-Aids that have silver nitrate in them, and that will be antimicrobial. It can also turn your skin brown. But silver in general, silver is always antimicrobial. Oh, the copper, silver, and gold are antimicrobial. So with silver, you can drink silver, something called colloidal silver, and it can treat stomach things. I forget the show. I want to say it was like House or something like that, or I don't know, one of those crime shows. And one of the things that they used to treat the patient one time was colloidal silver. And there's even a guy. Here we go. This guy drank a bunch of colloidal silver, and if you do that, this is what you may end up looking like. So it can turn your skin blue and whatnot. So kind of.
Ill in any other way?
I don't think so.
Or his skin was just colored?
Oh no. Let's see here. I can read the article. I have to look at the article. He just liked to drink silver. He carried it slightly to the extreme. So, but silver, like I said, copper, silver, gold, they are in general antimicrobial. One thing that has been debated about, I don't know why we don't do it, but door handles being copper, because then they would be self-cleaning. They also tarnish, which is funny. Brass or bronze is not antimicrobial, but copper metal itself is. Sterling silver is, that's why we have sterling silverware. So they actually are self-cleaning. And there is some research going into having silver fiber being put in underwear for astronauts and special forces people. So cases where you are not going to be able to shower for a very long time, that way the silver fiber can keep you cleaner longer, and in that environment, in that area. Gold also is antimicrobial, but it's expensive. So I remember I was house hunting one time, and one of the houses I went to was way out of my price range, and they had a silver kitchen, whatever, what is that called? Sink. There was a kitchen sink, and it was made of silver. I was like, well, it'll make it clean. You know, it's a self-cleaning sink, but it's kind of expensive. So, but yeah, so silver. Now, barium sulfate. I had the pleasure of drinking this stuff. This stuff tastes terrible. but they flavor it. It's used to be a contrasting agent for X-rays. So I had a stomach problem, and I had to drink the stuff, and then what it does, you can image your insides, specifically your GI tract. So you can see where your stomach, intestines, and whatnot are. So I took that, and they injected me with iodine. So you can inject with iodine, and then take an X-ray. The barium will show you where your GI tract is, and the iodine will show you where your blood vessels are. So, and I specifically had a CT scan, which a CT scan is it's just a bunch of X-rays. They slice you up. They shoot X-rays, and it's like a big donut. This big donut, and they put you on it's like a bench, and they stick you in and they stick you out. They tell you to hold your breath, and it's super fast. And I like them, but I mean, I've only had one, but it's a pretty hefty dose of radiation. So my dose was 400 milligram. Question?
Why did the hold your breath?
Because if you're breathing up and down, you can move your insides.
Oh.
Yeah. If you ever get an MRI, I had an MRI done on my neck after I had a car accident, and I had bulging discs in my neck. I think they've since receded, but when I was getting the MRI, they told me not to swallow. So of course I felt like I had like an ocean of water in my mouth. Like, all right, don't swallow for the next 5 minutes. I'm like, oh geez, Then I started salivating. It's like, so they tell you that crazy stuff like that. But yeah, well, that's what it's used for. Barium sulfate, contrast agent. Tastes terrible. Calcium sulfate, medically used to make plaster casts. No one ever makes plaster casts anymore. But where you can use it is in art. So when I lived on Oahu, I took a class at Manoa called bronze sculpting. So that was a fun class. It's too bad we don't have it here. Has anyone ever used the lost wax method for making sculptures? Okay, so the way you do that, the way you do a lost wax sculpture, you make a sculpture out of wax first. So let's say I want to make like a skull. So I'll make a skull out of wax, and then I'll put, now I remember the name of it. It's called a smudge. I couldn't remember what the name was at last class. You put an irrigation system in it. So you take wax and you attach it to your sculpture, and the irrigation wax is called smudging. And then you take that and you put it in, you put chicken wire around it, and you put plaster. And the way you make plaster, you take calcium sulfate and you mix it with water, and it gets hot. So you take you fill a bucket half full of water, and you dump in plaster until you get an island starting to form in the middle. Then you start wishing around with your hands. It gets hot. It makes this kind of sludge, slurry kind of stuff. And then you pour that with some sand. You can mix it with sand and other stuff, and then pour that in with chicken wire. You kind of put that around your sculpture plus the irrigation channel. And you seal it on the bottom, and you have the wax sticking out the top. And you take that and you throw it into a kiln. That's called an investment. And when you're done with that investment, you take it out, and you like with an axe and a sledgehammer. So you have to take the axe and you have to cut through the chicken wire. So it's a lot of fun. You're out there whacking this thing, and you can whack away all the concrete, or it's plaster. Whack away all the plaster, and you're left with the. Oh, I'm sorry. After you bring it out of the kiln, you pour the molten bronze into it, I should say. So I missed that step. Sorry. Yeah. Otherwise, I just invented air, So you have the investment, you pour the molten bronze into it, and then and you can do it pretty much right away. I mean, it cools pretty quickly, and then you can take it and you can whack it. Only thing you can squirt it with water too, because then it causes the thermal expansion to crack it. And that's fun though. I always like doing that. And then you cut off the irrigation system, and then you have the sculpture, and you polish it up after that, and you can add patinas that color the surface, kind of thing. So that's how you make wax sculpture, or make bronze sculpture using the lost wax method. So that was a fun class. Like I said, too bad you can't do it here. But if you go to UH Manoa, I recommend that class. So, but of course we So plaster used to use plaster casts. Now we either use fiberglass, or they don't. They use either some sort of like plastic or like straps, or maybe not even plastic sometimes. I sprained my ankle, a second-degree sprain, and I got an ankle brace. It was just nylon and Velcro. That thing was great. I couldn't walk, and then I put the brace on, and suddenly I could walk. You know, talk about instant helping me. I broke my hand one time, and I was put in a fiberglass cast. And man, have you ever had one of those? It itches. You always daydream about sticking something in and scratching your arm. It itched really bad. But like I said, we don't use plaster anymore. Nowadays, sometimes even like for a broken arm, they'll put like plastic, and then you can like tie it or something like that and protect it that way, and then take it off and shower, which would be heavenly. But calcium sulfate's still used for art. And potassium permanganate. This is antimicrobial, especially antifungal, used to treat trench foot. If you have really bad fungal infection in your feet, you can treat that using potassium permanganate. Has anyone ever seen the TV show Naked and Afraid? So that's one of my guilty pleasures. And you can take two things from the civilized world. One time, one of the contestants, she took potassium permanganate to use it as water purification and treatment for topical ailments. So I personally would get a machete and a fire starter. That's probably what I would pick in that show. But hey, why not potassium permanganate? So score one for chemistry. Then, this stuff is purple too. Potassium permanganate's purple. And it turns everything purple. If it's a liquid, it's okay. If it's solid, if you put that stuff, it can like put on a piece of wood, it'll catch the wood on fire. So it's pretty reactive. Potassium iodide. So we use this as an antiseptic and also to prevent radiation sickness. And this is a specific type of radiation sickness. So it may not affect us that much because of our diets. So we in America, we eat lots of enriched food. Our salt is iodized. They put B vitamins in everything. It is very rare to see an American with a vitamin or mineral deficiency. But if you look back to the former Soviet Union, in the Chernobyl explosion, that was in 1986, iodine 131 is created by a nuclear reaction, nuclear fission reaction. So nuclear power plants create iodine 131. Of course, it should be contained. It decays after 8 days. But if there's a rupture and material is released, then the people around can breathe in, people and animals, but we're focused on people now. People can breathe in iodine 131, and iodine is used by your thyroid gland. Your thyroid gland is right here, and your thyroid gland regulates your metabolism. It releases a hormone called thyroxine, and the more thyroxine you have, the higher your metabolism. It's kind of like your idle. When you turn your car, you have an idle. So if the idle is really low, your car doesn't warm up as fast. If it's really high, it heats up faster, burns more gas. So if you know the TV show South Park, so Kenny was thought to be hyperthyroid. It was suggested that Kenny might be hyperthyroid. People that are hyperthyroid have a really high metabolism. They tend to burn off all their body fat, or most of their body fat. That's why Kenny was always bundled up. He was always cold because he lost his body fat due to hyperthyroidism, perhaps. So there's the other way around. There's too little thyroxine, that's hypothyroid, and those people tend to be lethargic and kind of obese. So it could be from a thyroid condition. What's that? Cartman. Oh, he might have had something else. I forget what he had. Maybe Cartman was hypothyroid. He was pretty lazy too. I don't know. Perhaps. South Park due to thyroid. And there are some autoimmune disorders, so Hashimoto's and Graves' disease, where your body attacks your thyroid. and that usually causes hyperthyroidism. It also causes mental anguish. So people have trouble with that. And the treatment for those is typically to blast your thyroid with iodine 131. So you can hit the person with a lot of iodine 131, and then the radiation will destroy the thyroid, and then after that happens, you give the person thyroxine then via pill, so hormone replacement therapy. And if anyone's ever known anyone that's gone on, had to take the iodine 131, you have to go on a diet specifically before, because we in America, we have so much iodine in our food. So whenever you have processed food, it's going to have it. Anytime you have salt, so some salt doesn't have it. Kosher salt does not have iodine in it, but everything else does. Any milk product, they use iodine to clean the lines in the milk. So in frequently even soft drinks. So a lot of times iodine is used to keep those lines fresh. So you can't have any soft drinks, can't have any, and this is if you're going to be treated with iodine 131. So you have to get rid of all the iodine in your body so you can upkeep that 131 into your thyroid. And basically all you can eat is meat and fruit. So everything else you can't really eat. And I guess it's a good way to lose weight. But and it's also suggested that some of the religious dietary laws were to get iodine in your system. So if you don't get it from iodized salt, you can get it from ocean fish. So seafood, especially from the ocean, has iodine in it. So that's why Christianity used to be every Friday. You should eat fish on Fridays. It was really for dietary to help, because they noticed that people that eat fish tend not to get as lethargic and get fat and that kind of stuff. Well, they couldn't really get fat back in the day. They didn't have that much food, but people are healthier when they eat fish. So let's make them eat fish every Friday, just to be good, good for health. Although there are some interesting things. What they consider fish, like a capybara, for instance, is considered a fish religiously, because it spends all its time in water, so it's a fish. So you can eat capybara on Fridays at Lent, in case you ever find yourself in South America. Okay, so let's go back to the potassium iodide. So the people in Soviet Russia, or I guess it was Ukraine, so people in Ukraine didn't have the American diet full of enriched materials. So when the Chernobyl exploded, they breathed in all that iodine, went right to their thyroids, and they had some issues from that. But we stockpile it here in case there is a nuclear attack. They'll hand you a pill. It says, here, take this. You should take the pill. It's potassium iodide. It's to protect your thyroid, and it protects you from radiation sickness. Does that mean you said, all right, well, you know what, I want to be sure that I don't get radiation sickness. I'm just going to keep on taking iodine. That's a bad idea. That will cause a disorder called iodism. So where it also will cause lethargia and other health catastrophes. So this is moderation. So iodine, too little is bad, too much is bad, somewhere in the middle. And we as Americans, we're pretty good. And because we eat our iodized salt and our processed food. So if you're eating potato chips, you're getting your iodine. Going and eating French fries, you're getting your iodine. So unless you go on a meat and fruit diet, then that's probably only because you're either eccentric or you're going to be treated for iodine 131 for some sort of autoimmune disorder. So, and lithium carbonate. So I guess let's see here. You guys are in my lab, and some of you aren't, but some of the things I talk about lab, we're talking story, and I feel very old sometimes. Although the noon class did know who Nirvana was, and apparently Nirvana is still okay. So it's not too old yet. But Nirvana has a song called Lithium, if you recall. And lithium carbonate is one of the first mood stabilizers, mostly for bipolar, manic depressive disorder. So manic depressive is a type of bipolar disorder. There's a bunch of different types. Manic depressive is one. And what lithium carbonate does, it tends to even out people's moods. So it's a mood stabilizer. And magnesium sulfate. So actually, all magnesium salts, so magnesium sulfate, magnesium hydroxide, they're all laxatives. So they're all laxatives. And magnesium sulfate used to treat a specific condition called eclampsia during pregnancy. And magnesium hydroxide can also be used in acid. Magnesium sulfate Epsom salts is also a laxative. So if you eat that stuff, it can help clean you out. So the way antacids work, so there's a couple different ways antacid works. So magnesium hydroxide and sodium bicarbonate, we don't use sodium bicarbonate for antacid. This is too old. I don't know why Tro didn't change this, but common antacids, magnesium hydroxide, also known as milk of magnesia, also known as Rolaids. So Rolaids is solid magnesium hydroxide. Another one is Tums. Tums is calcium carbonate. So magnesium hydroxide and calcium carbonate both work by just neutralizing the acid. You have a stomach ache, you eat those, stomach acid gone. Kills it right away. Tums can also cause constipation. Magnesium hydroxide can treat constipation. There's also Pepto-Bismol. Pepto-Bismol is bismuth subsilicate. It works by coating the stomach. So that coats the stomach with the bismuth subsilicate. It can also turn your tongue black. So if your tongue turns black after eating it, that's okay. I had a student that freaked out about that one time. She was asking me, is that natural? I'm like, yeah, that's totally fine. Don't worry about it. So, but there are other ways to stop acid in your stomach. There are, so one of the more common is to take an antacid, just a tablet right away. There's also H2 blockers, and there's proton pump inhibitors. So those are the 3 drugs that we have right now. And mind you, much of this that we know about the body is called the physiological black box. We really don't know how it works, and we kind of guessed, and we have these ideas how they work. We have kind of semi-based, well, it's based on observation, but we give these pathways names, and what do these pathways look like? Can you show me these molecules? We have no idea, but we try our best. That's why we can't just scan you saying, all right, we need you to send this molecule in your body and that'll fix all your problems, because we don't know, we don't have that knowledge and technology. Well, we have the technology to make the drugs, but we don't have the knowledge yet how it all works inside the body. And that's what I mean, the physiological black box. Like if we pull a protein out of our bodies, how do we do that? Well, we rip the cell out of our body. Say I want to study a liver protein. How do I do that? I rip the cells out of my liver, and I crush the cells, and I separate it out, and I find the protein. Then I look at it in a test tube. Does that mean that the protein's going to behave the same way inside the cell, inside my liver? Like, we don't know. We don't know. Maybe it does. We just don't know. And then how do you track things inside the body? We kind of guess these things. So let me give you an example. The H2 blocker, so H1, let me talk about H1 blocker real fast. H1 blocker, that's a histamine. H is for histamine. Histamine blocker 1. And so what is a histamine? Well, let's say, well, I'm allergic to mold. And let's say I walk into a room that's full of mold, and if I'm there for a while, my body will say, oh, this is mold. I don't like that. I'm going to release this chemical called a histamine, and what is this histamine going to do? It's going to make my eyes water and my nose start to run. That is the histamine response. In severe cases, it can cause anaphylactic shock. That's when your throat closes up. So, but how can you stop that? You can take a histamine blocker, an H1 blocker, like Benadryl or Claritin or Allegra. What those do is those stop the histamine from being released. It's a histamine blocker. Therefore, if I know I'm going to be somewhere where my allergy is going to pick up, I take an H1 blocker, and then it won't be as bad. So prevent that. H2 seems to work. We don't really understand the pathway completely, but we know if you take an H2 blocker, it drops the acid level in your stomach way down. Pepsid is a H2 blocker, so is Zantac. Those are 2 H2 blockers on the market. Then there's a proton pump inhibitor. Proton pump inhibitor works by the way that your stomach makes hydrochloric acid is it rips a hydrogen off of a water molecule in your bloodstream, and it pulls the hydrogen ion through the stomach lining into your stomach. And it makes your blood slightly more alkaline, makes your stomach more acidic. And the way you can really decrease your stomach levels of acid is do a proton pump inhibitor, and that shuts those down, and then basically your stomach turns off almost completely that way. So I'm one of the lucky 1% that can't take those, though. So I found that out. But one of my problems is that if I take that, it more or less shuts down my serotonin production. So your stomach makes a lot of serotonin. So serotonin is a happy chemical, and you get serotonin when you eat. Your body rewards you by eating tasty food. You eat Halloween candy, or donuts from Krispy Kreme, and your body's like, oh, that's amazing stuff. I'm going to reward you with these awesome serotonin molecules. And that's also what cocaine does. It ups your serotonin levels. So you can get really high that way. Also, a lot of the other uppers, so like MDMA, also jack up the serotonin levels. So your brain can also make it too, not just your stomach, but your stomach can make quite a bit. But anyways, back to antacids. So, but I also want to tell you other drugs. So if you want to study drugs, there's various drugs that do different things. We also don't know how it works. I mean, we kind of guess. What is a proton pump? Actually, I guess we do kind of understand proton pumps pretty well. The H2, that's one of those. What the heck is that? Kind of thing. Sodium bicarbonate, we don't use it as an antacid. What I use it for actually is as a toothpaste. So I use sodium fluoride. So what I do when I brush my teeth, and this is under my direction of a dentist, I take a little bit of sodium fluoride, like toothpaste, like a pea size on my toothbrush. If you ever see the commercials, even in the box, they show like this big gob on it that's like an inch long, and like you don't need that much, like a pea size, a little tiny bit. And then I put baking soda on that. Sodium bicarbonate is baking soda, and I brush my teeth with that. And the reason for that is it's hypothesized now, and this is an emerging field as well. It changes the microbiome of your mouth. So your mouth is full of bacteria, and it seems to be that if you expose your mouth to an alkaline environment, you will improve the microbiome of your mouth. Like I said, this is an emerging field where we're looking at not all germs as pathogens, but there is actually helpful and beneficial bacteria and other types of microorganisms that are beneficial to us, and that we're also looking, we have more bacteria than we have cells in our body, and there's a relationship that we have with the bacteria in our body. It dictates how we smell, for instance. So, and we're now trying to figure out, like, okay, maybe we should start treating people's microbiome, and also looking at certain activities like it depends on the circumstance, but like when you use alcohol hand sanitizer, sometimes that can be dangerous because it kills everything, whereas soap tends to kill tends to kill most of the bad bacteria, most of the bad germs, and leaves quite a few intact. Actually, even washing your hands with water gets rid of a lot of the pathogens anyways. The reason for that is, so right now, if you look at me, my skin, I'm covered in bacteria. Okay, I'm completely covered in bacteria. Why am I covered in bacteria? It's part of my immune system. So let's pretend I'm a terrorist and I want to carry a bomb into the inner city. So I'm in the suburbs. I'm looking like I'm an upcountry, and I want to carry a bomb down to Kahului, and I'm going to ride the bus to get there. How can you make sure that I don't get my bomb to Kahului? If the bus is jam-packed full every time I want to get on, I'm going to get on the bus, like, oh, this one's full, got to wait for the next one. Oh, that one's full. If you're covered in bacteria, good bacteria, you can't have the pathogens. They can't find places to take a hold. So it's, in a way, it's part of our immune system to have these pathogens on this. And there's also good bacteria that are just, it's good to have around, and not even just part of the immune system. It's good for your body to fight some of them. Because if you don't, especially when you're young, your body then starts to attack itself. So some autoimmune disorders happen because people have grown up in too sterile environments. Your body needs to be trained on how to fight pathogens. And I'm at the age, you guys are all in your late teens, early 20s, right? So I'm supposedly have the best immune system. So 30s and 40s, you're supposed to be your top of your immune system lives. So, but you'll get there, hopefully. Someday you'll be just like me and brag about your wonderful immune system. So, but that's an emerging field, all this stuff with the microbiome. And let me talk about teeth. I'll get back to sodium bicarbonate. But this is actually kind of a controversial topic about sodium fluoride. Some people feel very strongly about this. But so here in Hawaii, though, we do not fluorinate the water. So the military bases do, but the municipal water does not. And also, Hawaii has one of the largest rates of cavities. And especially when you're young and you're developing, if you're exposed to fluoride, your body can form the tooth enamel with fluoride in it. So tooth enamel is a mineral called hydroxyapatite. It's calcium, phosphate, hydroxide. There's some ratio. What fluoride does is it replaces the hydroxide and hydroxyapatite, and it makes the tooth enamel stronger and less soluble. So it's hard to dissolve. So your mouth tends to be acidic, and it can dissolve your tooth enamel. So it's hard to dissolve if you have fluorinated teeth. It's also harder, so you can eat more, I don't know, Jolly Ranchers or something, right? So it's not going to damage your teeth as much because they're harder. Sodium fluoride also kills bacteria, so it's like 3 effect. So adults don't need it as much. Children need it more, but adults still benefit. You're like, oh, my teeth aren't growing anymore, and I'm not making more teeth. I don't need it. Not entirely true. Our teeth do remineralize. So we can grow enamel back in our teeth. It's not like we're given so much enamel and then we slowly lose it as we die. No, our mouth, our saliva has the ability to remineralize our teeth. So, and that effect is most pronounced by the formation of tartar. So tartar is tooth enamel. It's the same stuff, hydroxyapatite, but it forms over plaque. So what is plaque? There's 2 terms for plaque, and there's the plaque that's in the circulatory system. That tends to be lipoprotein, so cholesterol and protein stuck in your blood vessels. So that's different than the plaque in your teeth. The plaque in your teeth is undigested food and sugars and bacteria. And then our saliva can remineralize. If it sticks around for a while, our saliva can remineralize that, coat it with tooth enamel, and then it's stuck there. And you can get rid of it because, the dentist has to go through with the little scrapey tools and scrape it out. So it's hard to get rid of because it's tooth enamel, basically. It's the same stuff. But of course, our saliva can replenish our teeth. And so having fluoride there can replenish the teeth stronger. So it tends to be a losing battle. I mean, it's not like we tend to, of course, our teeth tend to wear it over time. But I mean, our saliva slows it down. So it's still beneficial. We're looking to see if we can actually grow back thicker enamel. So that's another term of research. So they're looking to put, how are we doing it? We're adding more materials that are used, the phosphate, for instance, in the toothpaste, seeing if they can grow back enamel at a faster rate. It'll also grow tartar at a faster rate. So you have to make sure you're clean to do that. Okay, so of course the fluoride, though, it is a moderation, because a little, like no fluoride, well, if you have no fluoride, then you just have normal teeth. If you have a little bit of fluoride, you have harder teeth that you tend to have fewer cavities. If you have too much fluoride, it can damage your bones. So you can get the fluoride, can go in your stomach. If you eat too much of it, it can turn into hydrofluoric acid, which can dissolve your bones. So, I mean, there is an argument against fluoride, and there is certainly an argument against too much fluoride. But fluoride was discovered by a town in Colorado, that there was a lot of natural fluoride in the water, and all the people they basically had no cavities, and the dentists were like, why don't these people have cavities? It was the fluoride that was in the water. So they're like, oh, we should put fluoride in everyone's water. So and that's kind of where we're at now. So some people feel very strongly about it. So, and I hope I don't get hate mail because of it. So, but I put fluoride in my teeth, kind of thing. And let me go back and talk about sodium bicarbonate. We don't use it in acid. It can be used to treat acidosis. So acidosis is the acidification of the blood. Blood's pH tends to be around 7.4. If it's too low, if it's below that by about 7.25, that is known as acidosis. And you can also go above, that's called alkylosis. So alkylosis tends to be much easier to treat than acidosis. Alkylosis tends not to happen as much. Acidosis tends to happen more frequently. And it's a little harder to treat. So you might have heard this before, like maybe you've heard of the word ketosis before, also known as ketoacidosis. That's if you don't take, if you're in a state of starvation, basically from lack of carbohydrates, your body can go into ketosis or ketoacidosis, and your blood becomes more acidified. If you are doing that intentionally for a loss of weight, drink lots of water. So, and the reason is that the way our body gets rid of acid, the two organs that gets rid of acid in your body are your lungs and your kidneys. So urine should be acidic, and that's where we get a lot of our acid out is through urine, and the other is by exhaling. So treatment for alkylosis is pretty easy. Alkylosis, all you gotta do is hold your breath, because carbon dioxide will turn into carbonic acid in your blood, and that's acid. It will lower your pH. So alkylosis is relatively easy to treat. Acidosis, on the other hand, it's not as fun. For severe acidosis, they can inject you with this. Next semester, we'll learn that our body has a buffer that uses sodium bicarbonate and carbonic acid to regulate the blood's pH. And I've had acidosis once. It was not fun. And one of the symptoms that you get with acidosis is hyperventilation. That hurts, by the way. I didn't need to have, well, the treatment for hyperventilation is to breathe in the paper bag. I was able to, like, I had to fight the instinct. But I got it from the volcano. I was at a conference at KMC, and then a new rift opened up, and there were lots of sulfur. We were there for several days, and after a couple of days, I started getting acidosis. I self-treated by drinking a ton of water, and then I had my kidneys cleared all out. But it was not fun. But hyperventilation, that raises your blood's pH. So when you hyperventilate, you're releasing lots of CO2 by hyperventilating, and the danger with that, someone who does not have acidosis, it is alkylosis, and how you treat someone is you have the person breathe into like a bag, so then they can reabsorb the CO2, so that way they don't go into a state of alkylosis. It's very difficult to die from hyperventilation. It's possible, but it's very, very unlikely. So sometimes I hyperventilate myself, like if I'm lifting weights or if I'm going underwater for a while. That's just to raise your blood oxygen levels really, really high. But in general, though, like I said, it is a symptom of acidosis. But severe acidosis, you can inject that in your bloodstream. Don't do it at home. Only do it at a hospital. The sodium bicarbonate is not pharmaceutical grade that you get, from Island Grocery and Safeway, right? So, okay, last one here is zinc oxide. Zinc oxide can be used as sunscreen. So I'm all about sunscreen. I don't like zinc oxide, but because it clogs my pores, basically, and it makes me look like a ghost. I'm already white, as is. I don't need to look any whiter. Titanium dioxide is another mineral that you can use to block out sun. It doesn't affect me because I'm so fair, but for darker skinned people, it can make them look blue or purple, supposedly. So I prefer organic sunscreen, not the FDA organic hippie stuff. Organic is in carbon containing. So that's the stuff that I mainly use as the organic stuff. I don't surf, but surfers like this because among other things also it can protect the reef. So some organic sunscreens can damage the reef. So we're working on that right now. But that's how we doing. Anybody have any questions about this chemistry and society stuff with what we use these ionic compounds for. Yes?
Do they have zinc oxide in deodorant? Or what?
They can. You can also have aluminum salts in deodorant, so depends.
Why would they have those in
They can act as antiperspirants. Well, there's two types of deodorants. There's deodorant, which is just a fragrance, and then there's antiperspirant deodorant that stops the sweating. There's two types of sweat glands in your body. There's epicrine, which is everywhere except for your armpits and your groin. Those have a different type called apocrine sweat glands, and they release proteins alongside of sweat. Sweat is mostly just sodium chloride water, but the ones here and here, they release proteins as well. And an issue with that is then we have symbiotic bacteria that eat the proteins and then cause body odor. Although it's part of humans' pheromones. Well, I'm not sorry, pheromones. It's part of our sexual compatibility test. So because the symbiotic bacteria that we have in our body will the certain smell determines the type of microbiome we have, and the type of microbiome also is an indicator of the strength of our immune system. And generally speaking, if you like the way someone smells, it's because it's more female interested in male. That if they like the way that someone smells, it's because if there was a pairing between the two, the offspring would have a stronger immune system. So it's a way for a female to find a stronger genetic immune system mate. It's also a way to prevent incest. Because if you're in a tribal situation, maybe you don't know who's mama's baby, daddy's maybe kind of thing. You might have like whatever relations. You might have someone who's actually a closer relation than you'd expect, and then the person the smell tends to be repulsive to a female. So a female is going to find a male relative smell repulsive in a sexual sense. So, or so some studies suggest. I haven't tried it myself, but that's what some of the genetic research is suggesting. Certain male characteristics are also seen as immune. So having a square jaw, for instance, is actually is unfavorable for immunity. So it's kind of like saying, like, I can handle this. If I can handle this disadvantage, then, and I'm still alive, then, you know, I'm a good partner, kind of thing. I'm a brawny man. So that's all on YouTube. Any other questions, or so? Okay. Alrighty. Back to chemistry and not potential mates. But it's all science. And I'll look it up. Okay, so now I'm going to talk about covalent bonding, and we'll talk lots and lots and lots about covalent bonding. So it won't just be today. It'll be next class, pretty much on until the end of the semester. But here is what's known as a Lewis dot structure. I've mentioned this before, but fluorine has 7 valence electrons. And 2 fluorines come together, and they can say, so one fluorine can approach the other, and you're like, you know what would be really cool? What if I have 7 electrons, you have 7 electrons, what if we share 2? Then if you look at me, I've got 8 electrons, and you have 8 electrons, but so we're going to share these 2 here, and we're going to keep 6 ourselves, but like I said, it seems like we both have 8 electrons. So that's what's called, also known as the octet rule. Things tend to bond to 8. And that they bond to 8 because it's lower energy. And rather than write all these dots, we tend to understand that fluorine does have the lone pairs sitting there, and we just draw a line, and the line means that 2 electrons are shared. Likewise, with oxygen, each has 6 outside valence electrons, and so the oxygen's approach is there said, hey, what if we kept 4 and we shared 4? That way I'd have 8 and you'd have 8, and we're both happy. And they do that, and so oxygen shares 4, and we call it a double bond, or 4 electrons and 2 lines. So we understand 2 lines means 4 electrons shared. Likewise, nitrogen can share 6 electrons, or having a triple bond, so the 3 lines denote that 6 electrons are shared between the 2 atoms. So, and this is also, in this case, this is a very good beneficial partnership, and everything is shared equally. So the electrons are not dots. They're this fuzzy cloud of existence. And when I say, like, okay, we have 6 electrons being shared, does that mean there's dots just between them? No, it's a cloud. And electrons can be in more than one place at the same time. And the electrons then kind of form this cloud between them, and half of the cloud is around this nitrogen atom, half the cloud is around that nitrogen atom. Actually, for this one, it's more of a cylinder. It kind of forms a cylinder between the 2 of them, with more density around the nucleus. But it's a very even cloud that way. And what about what if we don't have the same atom? And this next trend, I mentioned this before, is called electronegativity. Electronegativity, this end is the positive and higher up. It's the same trend as first ionization energy. So the trend is further to the right and further up means more electronegativity, and you exclude the noble gases. So electronegativity is the ability to draw electrons, the ability of an atom to draw electrons to itself. So an analogy to that, has anyone ever seen a celebrity in real life? Like, yeah, I mean, I think I've only seen a few. So I've seen Eddie Murphy, and I went to a taping of the David Letterman show, and there was an actress, and I forget who it was, but man, she was beautiful. You know, I mean, and Eddie Murphy, he was really handsome. You know, I mean, they just have a glow about them. So if you ever see a celebrity in the street, what happens? People just kind of flock to them. Even if they weren't famous, I think that would happen. I mean, because they have such a glow and presence. So certain atoms are like that, like fluorine. Fluorine is like the Brad Pitt of the elements. So electrons see fluorine like, man, that's a +7 center, really tiny atom. My electron density is just drawn towards that tiny +7 center. So when fluorine bonds, it's like an electron vacuum cleaner. Electron density flows towards the fluorine. So, and then over here you have cesium and francium. They're like, oh, electron, you want my electron? Here, take it. Plop. It just pops right off. The electrons couldn't be happier to jump off of cesium kind of thing. So it's not as good as holding on to its electrons. Electrons like, ooh, cesium or fluorine. Like, ooh, fluorine, draw me towards that. So when cesium and fluorine meet up, the electron doesn't have a chance. It jumps right off and goes to fluorine. So that trend is electronegativity. And you can see it's not necessarily a smooth trend. And you can also see here in the middle that you have gold with an electronegativity of 2.4, and you have phosphorus 2.1. Does that mean that gold is a nonmetal and phosphorus is more metallic? No. So phosphorus is definitely a metal. I'm sorry, phosphorus is definitely a nonmetal, and gold is definitely a metal. Metals can form covalent bonds with themselves and with nonmetals. We'll talk more about that later. But it's not like we can only have ionic bonding with metals and nonmetals. This I always thought was kind of interesting, this kind of stuff, that they have that electronegativity there in the middle of the periodic table like that. But be careful, let's talk about mates and stuff. Next concept is a polar covalent bond. Polar means unequal sharing of electrons. Why is it polar? Well, And hydrochloric acid or hydrogen chloride, you think with this one line here that what would happen is you think that the electron cloud is like that. Okay, let me draw it bigger. So if you have HCl, you would think that the electron cloud between the two would be like that. If I'm an electron, that one electron should be shared like that. How it's really shared is like that, but it's much heavier around the chlorine. So the chlorine is able to draw electron density away from the hydrogen, and then because of that, there is a slightly positive charge here and a slightly negative charge there. What do I mean by slight? I mean less than 1.6 times 10 to the minus 19 coulombs. That's the charge of a proton and or electron minus for that. And another analogy for that is that it's like a blanket hug. So you have hydrogen chloride here, and so where maybe you've shared a bed with someone, and maybe the person is a blanket hug. So you think, okay, we should share the blankets equally, and we'll be nice and warm. Instead, maybe it's you, maybe it's the other person, maybe you steal the blankets and you're nice and warm and toasty, and the other person's freezing, or maybe you're the person that gets the shaft. You can see your hydrogen's got a little bit of blanket coverage, still pretty cold. Chlorine, very happy and warm. So that's the electron density flows towards the chlorine. And because of that, you have a positive and negative end, so we call that a polar bond. Just like, although the Earth has a magnetic field, the North Pole is a positive, South Pole is negative, but that's a magnetic field. It's different than electronic. This is an electronic field, but we still give it the word pole. We still have the poles in an electronic field. So called a polar bond, just like the polar bear is at the North Pole. And we also have, what are these things called? Penguins. Penguins in the South Pole. So you'll never see penguins and polar bears together except for a zoo. All penguins are found in the southern hemisphere. Anyways, well, and I personally, I disagree with this chart, but I'm going to teach it anyways. And the reason why we teach it is because of organic chemistry. So what organic chemistry says is that for a small difference in electronegativity, up to 0.4, that is a covalent bond. Why 0.4? That's the difference in electronegativity. I should also say this is known as Pauline's electronegativity. There's different types. Pauline is the ones that use most frequently. If you see electronegativity, they usually mean Pauline's electronegativity, unless they specifically say it's someone else. But 0.4 is the difference in Pauline's electronegativity between carbon and hydrogen. And organic chemistry says that carbon and hydrogen is a completely covalent bond. It's not. And they contradict themselves later on because they say that oxidation, so removing electron density, is when you rip a hydrogen off of a molecule. So they're admitting that hydrogen adds electron density. How does hydrogen add electron density? By being less electronegative, and it gives its electron density to the molecule. So, but I'll get off my high horse. But the easiest way to remember it is, if it's the same atom, it's a completely covalent bond. If it's a different atom, it's a polar covalent bond. And later on, we'll talk about molecule shapes. And if you remember that fact, it'll make your life much easier than trying to memorize all the electronegativity and then the difference in this chart here. And this doesn't even work all the time, too. So a large one is an ionic one. You can have ionic character. There's blurry lines between these two. But the idea, though, is a perfectly covalent bond, everything's shared equally. Ionic bond is when electrons are donated from one atom to the other, and then in between is a polar covalent bond. But truth be told, it's only when the same element, so if you remember the same element, it'll be shared equally. Here, it's two different elements, it'll be shared unequally. And ionic does tend to be more frequently with metal and non-metal, but there are other cases for that, which we'll talk about later. Mostly not in this class, though. Does anybody have any questions? Alrighty, and then it's time for me to shut up. So, and there's my shut up alarm.